So let's start with block diagram, which helps us understand what are the different components that are present. And in the NMR spectrometer, you have three individual components, as you are able to see. One will be in the magnet, as written here. The other will be the RF circuitry and the receiver circuitry. These two would be a part of something called a console. And this is the computer with which we end up interacting when you're actually in the NMR center and trying to set up your experiments. And there are different components to each one of this. So I'll go over one by one. So this is, as I said, this is the computer in which you will start typing commands. I'll try to show the software we end up using. If you're using a Bruker spectrometer, the software is called the TopSpin software. You'll be using the TopSpin software giving commands, which will then end up interacting with various hardware that are present in the console and therefore help you get whatever you want from the magnet and the probe. Let's start with the magnet here. There are different components in the magnet. The main components are listed here. The most important component of the magnet is called the probe. Although we list it under magnet, this is something that is detachable. Generally, probes are replaceable. You can have different types of probes. The probe is one where your NMR sample ends up sitting in. Okay, so let's assume this is your NMR sample. When you throw it in, it actually ends up sitting in the probe. The probe is one where you end up receiving signal for whichever nuclei that you want to see. This once again forms the heart of the NMR spectrometer, where the components in this critically decide which experiments are feasible for you and which are not. Then comes the shim coils. The shim coils are one can imagine these are electromagnets around the sample, and these help homogenize the magnetic field. Okay, of course, this is important here because we did not spend much time talking about the magnet. The B naught that you end up talking about is other most important component of this entire part, where the B naught helps you achieve a certain magnetic field strength. And this is achieved by the use of superconducting coils. Superconducting coils are one where when you reduce the temperature, they have almost zero resistance, resulting in the fact that you could have the highest of magnetic fields that could be obtained. Nowadays, there is a serious quest for people trying to achieve superconductivity at room temperature, and if it does happen, NMR would benefit significantly from it. The shim coils are in addition to this B naught, where the B naught helps you get the largest of the magnetic fields you could get. The shim coils around it would help you homogenize the magnetic field. If you remember, magnetic lines of force have to be as parallel as they could be, not something like this. So this would constitute an inhomogeneous B naught, while this constitutes a homogeneous B naught. The shim coils help you achieve this target of homogenizing the magnetic field. So therefore, you get very well resolved resonances. Therefore, you'll be able to do NMR at a very high resolution. This is the next component we generally attribute it as the lock. These are steps that you will also do in an NMR experiment. Hopefully, you will have a demonstration as we go forward. What this ends up doing is to use a nucleus that we don't end up exploiting most often and fixes the field and frequency with respect to each other. For instance, at a given B naught, you would know what will be the omega naught for deuterium. So therefore, which is going to be minus gamma D times B naught. So once you have a B naught and a gamma D is fixed for a given nuclei, the omega naught for deuterium is fixed. However, what ends up happening is that the B naught might end up drifting over a period of time. What do I mean by drifting? You have to write 11.7 followed by several decimals here. The last decimal could slowly start changing. Let's say 6th decimal could slowly start changing. So what that ends up resulting in will be loss of resolution. Once again, you will start to get broad peaks just because your B naught is not homogeneous. I mean, it's not constant as a function of time. So therefore, what we end up doing here is that we have an internal circuitry which keeps checking for how much ever the B naught drifts, the frequency for the deuterium is corrected. So for instance, whatever changes come up here, there is an internal circuitry that gives current to make up for the changes that come, so as to ensure that as you run the experiment, the B naught is more or less kept constant. So this process is what is called locking. In fact, it's called field frequency locking. So therefore, if you are able to see here, all these components put together ensure that you have a high magnetic field, and in the presence of a high magnetic field, it's homogeneous, and on top of it, as a function of time, the magnetic field does not drift. Under this context, your sample that sits in the probe can actually be characterized. So the next component that we'll be looking at here would be the RF component. The RF component is important because the computer, wherever you end up typing some commands, will be sent forward. For instance, in the computer that you have, you might clearly indicate you have a 90-degree Y phase pulse with an acquisition. But remember, this has to be translated back in a way where the probe can understand. That is what is being achieved by this RF circuitry. So in this case, what you end up doing is that you write in a language that you understand in this computer, and that gets transferred to this pulse programmer, where whatever language you ended up writing here gets converted in language that the other electronics can understand. And you start applying the omega RF in this place actually. Remember, we had this cos of omega RF t plus phi. Of course, the phi we just set as the Y phase. And of course, there's also a B1 that you have up front. Not able to write here. So yeah, you have a B1 up front. The B1 is what is deciding whether it's a 90-degree pulse or whatever flip angle it is. Well, the omega RF gets added up by this frequency synthesizer. We'll see why it is coming back later on in the receiver as in a little while. So after you have that, you also have the RF transmitter, which is what ends up interacting with the probe. Once you apply the sequence of commands which you wanted to do, it gets transferred to the probe. So now, therefore, your sample ends up experiencing the whatever changes that you want to do, whatever perturbations you want to do, however you want to acquire it, are all therefore transmitted to the probe. After having done that, you applied your pulse, and the signal that ends up coming, which is your free induction decay, so we can try to say this is the pulse, the free induction decay will be obtained by the receiver. And the receiver also has multiple components in it. One of the main components here is called a preamplifier. We will at least learn about the preamplifier again in a little while. What this does is that the main difference between the pulse and the signal that you obtain is that the pulse is of very high power. However, the signal that you get is of very low power. I mean, in terms of current, you can think of measuring currents in milliamps. And you can think of current here as an amps. So therefore, what will end up happening, after you apply the pulse, you turn off for a little while and then open this up so that you don't get overwhelmed by the pulse that you ended up applying. Remember, after you apply the pulse, it doesn't immediately die. It also has its own time to not be present anymore. So therefore, that's called the dead time, where transmitter is off, so is the receiver, both are turned off. But after that, you turn it on so that you can acquire a free induction decay. Since the signal is of very low intensity, the preamplifier that is present increases signal as much as possible so as to improve something called dynamic range. Let's quickly talk about what is dynamic range. Dynamic range is one where, let's say you have a signal. Remember, you're going to have sample that has a lot of water. You're talking about 110 millimolar of H plus ions that are going to be present. Let's say the protein that you're talking about is present at 1 millimolar. So therefore, what ends up happening, the huge difference between the signal from water and the protein is going to be like 10 power 5 orders of magnitude different. So therefore, what we end up doing is to kill water as much as possible so that we can amplify the signal that we get. Even within the protein, if you are able to imagine, CH, CH2, CH3, you would see that CH3 is more intense than CH because you have 3 protons that are present. So therefore, what will end up happening, you will have a mixture of strong and weak signals that are present. So therefore, the range of signals that you get would go from weak to strong. Now, if you're only getting the strong signals, it could happen that you will never be able to observe any weak signals. On the other hand, if you are able to observe, if you're only observing the weak signals, the strong signals could be out of detection. So therefore, you have to carefully manage the range within which you will be able to capture both the weak and strong signals, and this is what is termed as dynamic range. The preamplifier helps you keep an appropriate dynamic range so as to ensure the weak and the strong peaks are kept within spectrum. If you use way too high a concentration, the signal ends up going outside the detector. You won't be able to see. So that could happen when you're setting up the experiment only to see weak signals. But the problem will be the strong signals will overwhelm the detector that you cannot see them anymore. So this is an important aspect in almost every spectroscopy, and NMR is not any different from that. So now let's get to the next component of it, which is called the phase sensitive detector. In here, I would like to allude to the fact of Fourier transformation, where you guys were able to see e power I omega it gave you a signal at capital omega I and no signal at minus omega I. The reason why I kept on writing both sides is to show the fact that you will only get a signal at plus omega, and this aspect is called frequency discrimination. So this means that you should be able to discriminate plus omega I from minus omega I. If you are able to plot it, you will realize that in some cases you might not be able to distinguish it. So frequency discrimination plays an important part of it, which is why if you are only obtaining the cos omega it part of the signal, you will actually get a signal both in plus omega I and minus omega I. So this is an important aspect. So this frequency discrimination is done by the phase sensitive detector. So what does that mean? You not only collect the cos signal, but you also collect the sine signal, which is what you get as e power I omega t, and therefore you're going to have a signal at plus omega I like this and minus omega I like this. So therefore, when you sum up these two, you're going to get no signal at minus omega I and only a signal at plus omega I. So this is a very important aspect where the omega RF that you had put in is actually subtracted from it. Remember, your signal is within a spectral width, and wherever your carrier was, you switched it from the spectral width plus omega RF. So you just subtract the omega RF, which is why this feedback is required depending upon how much ever you added. You subtract that to get the spectrum within the range that you have. And the audio filters are the next series of ones which help you cut any signal that comes outside the range that you want to see. This is important because NMR is a very sensitive technique. So therefore, these bandpass audio filters would help you cut any signal or even noise that ends up coming outside the range that you would like to see. The last component that's extremely crucial is called the analog to digital converter. As we have been drawing all the time, we have been drawing the FID as though it's a continuous function, right? So this is actually called the analog function. Unfortunately, we cannot determine every point on it. So therefore, what we do, we discretize it, meaning that we get a bunch of points. We'll discuss more about it as we go forward. Okay, so this component ends up converting your analog to a digital signal. So if you don't end up carefully managing your gain for the spectrometer, the strong signals will result in something called ADC overflow, which means that you have so much signal that the ADC is not able to convert. So let's say this is the range of ADC converter, you're going to have signals. If you have signals that are above this, it's going to throw an error that ends up coming. Now, therefore, this discretized signal is then given to the computer, where once again we Fourier transform to take a look at the spectrum. So now let's go to the next component, which is the magnet. Once again, as I said, I'm taking all the pictures from this Kavanagh textbook because they look beautiful. So if you go to an NMR center, what you're going to see is something of this sort. So what you see here is actually probably this one of the earliest 900 megahertz spectrometers. And if you're able to see the size of a human being there, the magnet that you're talking about is significantly huge. These are the legs of the spectrometer. So there's also one more leg which you're not able to see. Okay, so that's how big an NMR spectrometer could look. So this is a reasonably sized magnet. And what you see here is 700 megahertz spectrometer. And this is something called a cryo platform. We will come in a moment. The probe will be right below the spectrometer. The sample will be inserted from the top. You see how small the spectrometer is. This is the size of human being and this is the size of spectrometer. And what you see here is probably it's a 300 megahertz spectrometer that you're looking at. So larger the magnetic field you want, probably the larger size of the magnet you're trying to look at. Currently, the record stands at 1.2 gigahertz. It's not anymore in megahertz. Okay, so now that we have taken a little bit of look at how the magnet should be looking in reality, so let's quickly go to the schematic. Let's quickly go to the schematic and understand what are the different components. As I already mentioned to you guys, we are talking about a superconducting magnet. Superconductivity is actually achieved at very low temperatures, and in this case, it's achieved with the use of liquid helium as the source. So liquid helium can be cooled up to 4 Kelvin, and if you actually boil liquid helium, you can go up to something like 2.2 Kelvin or even lesser actually, depending upon how much you boil off. Right? So What you see here, so this is the solenoidal magnet, the black thing that you're able to see, and that's actually kept in a helium vessel. So that's where the liquid helium goes. The liquid helium helps keep the superconducting magnet at the desired temperature. And of course, outside, immediately outside the superconducting magnet, as you see, this is liquid helium, trying to show liquid helium here, and there is a separation here which ensures that outside that you also have a liquid nitrogen bath. Okay, so basically, in order to ensure that the helium doesn't boil off very fast, you have another layer which helps the nitrogen be available, because nitrogen gas and therefore liquid nitrogen is cheap. We end up trying to minimize the amount of helium, liquid helium that vaporizes by using a liquid nitrogen that's present right outside. And of course, you have a shield outside which we will of course be standing and doing our experiments. Nowadays, these shields are done in such a way that the magnetic field does not affect the person standing nearby. So generally they look for something called a phi Gauss line, and nowadays it's very, very close to the magnet, so we don't have to worry. But if you're looking at older magnets or still going for an MRI scan, you have to be very careful about the magnets. You should carry nothing that's magnetic.
Initially, in the early classes, we'd said the population dependence on temperature is very low.
Correct?
As in, then why are we trying so hard to keep the equipment at low temperature?
Very good question. We are talking about two different things here. All we are talking about here is to achieve a certain B naught, you are going to very low temperatures. On the other hand, if this is confusing you, whether our sample is also in 4 Kelvin, not really. Your sample is at room temperature, which you will see, which is where the probe comes in once again. If you take a look at the probe, this is actually where they are depicting the sample. And the sample's temperature and the magnet temperature are very different.
This
Okay?
is purely for superconductivity, is it?
That is correct. So the vibration legs that you see around, the huge things that I also marked in the big magnets, is to ensure that any vibrations that might come on a ground are dampened. This is important because when you put the sample in the spectrometer, you should never rest your hands on the magnet, because if you do that, it's going to push the magnet down. And you might wonder, okay, why are you so worried about it when you're not acquiring the data? Is because the moment you start moving the magnet a little bit, helium will start boiling off. The moment you start boiling helium off, more helium will boil off. But the moment the gas comes in, the gas would escape, which is where you have all these vents that are present. These vents are for nitrogen and helium. I think one will be for helium, the two others for nitrogen. Nitrogen will escape in one, and the other will be filling every week. On the other hand, you'll also have a helium port where you'll insert helium and the helium can exhaust through the other one. Okay, so one has to be very careful handling the instrument. Don't touch things that are not required to be touched. These are the shim coils that we were talking about. Okay, so these are all electromagnets right around your sample in order to homogenize the field a little better than whatever you get from the main magnet. But even before you have the RT shims, you also have something called cryo shims. Unlike the RT shims, which are managed by the user, that is you and me, the cryo shims are set up when the instrument is initially installed. The engineer who comes installs all this to perfection such that the magnetic field is as homogeneous as possible from the cryo shims itself. And any small changes that come up when you put different samples are taken care by the probe. The RF coil that you see here is the one that transmits and receives the signal. And if you're curious about how big the NMR tube is, we are talking about something like 5 millimeters outer diameter. Inner diameter is like 4.2 millimeters. And you're talking about a 7-inch tube. Okay. And you have 500 microliters of solution. So probably the height is about 3 centimeters that is present there. And the active volume or the active length of the coil is something like 1.5 centimeters. Okay, so we will come to the aspect why is that you need to have more sample than whatever is being acquired later. Once again, it helps in the fact that shims can be better done. So there you go. So that's the RF coil, and you're able to see the sample tube. And in addition, this NMR tube is not dropped as it is. You also have something called a spinner. You can imagine that's the spinner, and your NMR tube will look like this. This is where your sample is, and this is called a spinner. The spinner will have different colors, either this way or this way, and this is where you put the sample in, and you are able to see the spinner depicted here. Okay, and the way you get the sample in and out is by having an airlift. I think the airlift will be shown in the probe section, where you push air and the sample will shuttle in and out of the spectrometer. Spinning also is an aspect which helps you get better shims, similar to the fact that when you have more volumes, you will be able to get better shims. And the magnet, once again, which we saw in a little bit of detail here, is shown here. How does the magnet look? So far, what we have seen is what is a block diagram of NMR spectrometer and how does the magnet look. The magnet has different cryogens in order to ensure that the superconductivity is maintained at a low temperature. And the nitrogen is something which we fill every week. On the other hand, helium is something which we fill every three months or so. Never ever put the sample without the spinner. Spinner is extremely crucial because that is what helps the airlift push the sample out. If you don't have the spinner, the air will escape and your sample will always remain inside. So that's a problem. Spinner is utmost required whenever you put a sample in. And at the same time, make sure you lift the sample, meaning that in the software you end up using, you will have to type a command which will eject the previous sample, and then you have to insert the next sample by carefully removing whatever was inside and putting the next one inside it.
So what is the main difference between solid state NMR and solution state NMR? Is it based on the probe that we are using in both?
Lot of differences, except for the magnet. Even the magnet, the way the bore is present, wherever the bore is where your probe goes in. Okay. Generally, solid state NMR spectrometers have something called a wide bore because their probes are very different in size from solution state. So that is one of the main differences, but there are even more differences that come up. In a solution state NMR experiment, your sample is in the liquid state. And in a solid state NMR, you're going to have powders or crystals that you end up analyzing. The way you are able to nicely take a sample and put it in, solid state NMR is not like that. You will have something called a rotor where you will have a small hole at a certain angle. You will actually put the sample inside it and pack the rotor. Then you take the rotor, put it in. So these are huge differences that come up. And one of the major differences that come up is the angle at which the sample is present. In NMR, the sample is present parallel to the B naught. In solid state NMR, it is present at a 54.7 degree angle. And then what we do is that we spin the sample at say 20 kilohertz. There's a huge difference between this and this. If at all anything for 1D NMR, we spin at 20 hertz. For biomolecular NMR, we don't spin at all. We'll talk about the reason later. But for the solid state NMR, you spin at a very high speed, which is why solid state NMR is associated with almost always called MAS, magic angle spinning, solid state NMR spectroscopy. And generally they are attributed with the spinning speed. In this case, I get 20 kilohertz. There are nowadays rotors that can go up to 100 kilohertz. Solution state NMR predominantly is driven by proton detection. On the other hand, solid state is driven by carbon and nitrogen detection. So what you're able to see here is the magnification of this small portion here. Whatever you see here is what is magnified here. So basically, if you want to see the connectors that they're talking about are present here. So, and what you're able to see is that this is the VT air. So this is what helps you change the variable temperature. Let's say you want to run your experiment at 283 Kelvin. So the VT air will send in cool air such that you can reduce the temperature of your sample. And basically your sample will go nicely go and sit here. And the coil that I was talking about, observe coil, the observe coil is also the transmitter and the receiver coil. Okay. For, of course, in this case, let's assume observe coil is proton, decoupling coil is 13C, for instance. You have both the coils that are present. You have other aspects that are present. I'm not going to go into much of detail, but what you're able to see here is that any observe and decoupling circuitry is actually present within this probe. And for people to understand a little bit of what is this RF circuitry, I might want to go back to some basics that you might have learned in your 12th standard called the LC tank circuit. So this is one where, depending upon the capacitance and the impedance that is present here, you would be able to pick up a frequency, omega. The angular frequency will be given by 1 over square root of LC, where L is the impedance, C is the capacitance. It's called a tank circuit because similar to the ripples that would be present in a tank, whose frequency will be determined by the dimensions of the tank. Here, the frequency that you end up measuring from the circuit is depending upon the inductance and the capacitance that is present. Okay, so that is what helps you pick up a desired frequency. Remember, we have to apply pulses in that given frequency. Otherwise, you're not going to be on resonance and therefore you're not going to pick up signal. So therefore, this forms an important aspect. So what you do as the first step is to do something called tune and match. Let's say you put the sample in. What you try to do, you will be changing some of these values in order to make sure the frequency is matched between your sample and that of the probe, and the impedance is matched so as to ensure all the pulses that you apply are completely transferred to the sample. So this tune and match, where you end up changing the impedance, like the capacitance and the inductance of this coil, helps you ensure any pulses that you apply are completely transferred to the sample and not get reflected in the process. So this is a very important aspect, and one also has to remember that generally in our sample we tend to have salts that are present. If you have salts present, if you apply EM radiations, they could also start having something called eddy currents, which would have other effects. Remember, once you have a current, you have a magnetic field. Once you have a magnetic field, you could induce current, and it goes back and forth. And all this could end up reducing the efficiency at which you could apply a pulse. But overall, I hope I have given you enough understanding here, where there are quite a bit of engineering that goes in how the probe and how the magnet and how the entire console is all packed. So now let's finish off this session with one important equation. The equation here is the signal to noise ratio. So that is going to be given by a lot of factors. Let me write it so that I don't make a mistake. TSRS plus TA times RC plus RS TCRC. So what you're seeing here, this is the signal to noise ratio. The signal to noise ratio in NMR spectroscopy depends upon the number of spins that are present. You can imagine the number of spins is basically your concentration. More is your concentration, more is the signal to noise. And the most important thing is that signal to noise is linearly connected with the concentration. Meaning that if you double your concentration, you'll get double the signal to noise. If you triple your concentration, you get triple the signal to noise. It also depends upon the gyromagnetic ratio of the excited nucleus. For instance, in a simple proton one-dimensional NMR experiment, you're exciting the proton nucleus, and therefore you actually go with gamma e power 1. And gamma d stands for the gyromagnetic ratio of the detected nucleus. So therefore, it goes with gamma d power 3 by 2. So this is very important aspect, which is also why solution state NMR spectroscopy start from proton and detect in proton, because the excitation and the detection nucleus, if it is proton, you gain the maximum in terms of the gyromagnetic ratio. Of course, in the previous lecture, you might have seen an experiment where you started from proton and finished with carbon. In that case, you're going to have gamma h power 1 and gamma c power 3 by 2. Once again, we will see as we go forward to 2D NMR, which is why we will not prefer the carbon direct detect. We'll be going to proton and be detecting. And then it also depends upon the magnetic field strength that is applied. This is a race in the entire NMR community on who has the highest magnetic field strength. That's largely because the increase in magnetic field strength increases the signal to noise ratio in such a way where it doesn't not just increases linearly, it increases power 3 by 2. Meaning that if you double the magnetic field strength, you are not going to go as double, you're going to go as 2 root 2, which is about 3 times more than whatever you started with. K is called the filling factor, which accounts for any losses in signal that might happen just merely because of the fact that the sample and the receiver coil are far away from each other. So what people try to do, of course, this number goes between 0 and 1. 1 means you get all the signal, 0 means you get no signal. I think it's somewhere around 0.7 to 0.8 for most of the probes. What they try to do is to make sure the probe is packed as tightly as possible and the receiver coil is really, really close to the sample that is present. So therefore, this is carefully engineered to ensure that you get the maximum signal to noise ratio. The delta F that you're talking about is the bandwidth that you're going to be observing. It's slightly different from the spectral width you're trying to talk, but overall you can now imagine it goes close to the spectral width or slightly more than that. And you have a bunch of temperatures and resistance that the signal to noise depends upon. Let me start with the temperature of coil and the resistance of the coil. What do you mean by the coil? You're talking about the RF circuitry, the coil that is present there. At whatever temperature they are present, that will influence the signal to noise ratio. Higher the temperature, lower the sensitivity. And also you have the temperature of the amplifier. If you might remember in the block diagram, I mentioned about the preamplifier. If you are able to cool the preamplifier, you get better sensitivity. This is also done routinely in solution state NMR spectroscopy nowadays. It also depends upon the temperature of the sample and the resistance of the sample. Resistance of the sample basically comes from the fact that you end up using cations and anions which are conducting. If they are conducting, they are going to have a resistance. So therefore, the more the salt that you end up having, it might end up changing the signal to noise ratio. Now comes a very important aspect of cryogenic probes. In cryogenic probes, what is done is that they reduce the temperature of the coil in addition with the preamplifier, which helps you get sensitivity boost theoretically to the amount of 4 times. This comes at a little bit of a cost of the K value, but overall people end up getting at least 2 to 3 times sensitivity boost when they use RT probe versus a cold probe. For solution state NMR spectroscopy, this is a deal breaker where biomolecular applications are feasible at very low concentrations of the molecules that you want to see. As I have kept on repeating, insensitivity of NMR spectroscopy is a big limitation. The cryoprobe has definitely alleviated this problem to a significant extent, where nowadays people are also able to do their studies at as low as 10 to 50 micromolar of labeled substance. We'll also see how signal to noise could be improved with isotopic labeling, but one can actually push down the concentration to a very, very large extent. And what one is able to see here is that the signal to noise depends upon so many different factors. So one has to be very careful in the way an experiment is chosen, meaning that where you excite, where you detect, the concentration that you end up using, the spectrometer field strength that you're working, and the kind of probes that you end up using. Similar to the magnet being at 4 Kelvin, your probe is at 20 Kelvin. Your sample is still at 298 Kelvin, or whatever temperature you want to run it at. So these are very different things. All that the probe helps in is to reduce TC and RC, where that helps you in getting better signal to noise ratio. So what you're able to see here is once again an 800 megahertz magnet, and you have a separate helium pump. The moment you want to go to 20 Kelvin, you have to use helium. Helium is expensive. This is the console I was talking about. This is the magnet we were referring to. These are the legs, these blue things. Not able to see the back leg, but I think you see a little glimpse of it. The probe is right there. You are able to see the connectors. And in here, this is actually a cold probe, which helps in recirculating helium in these pumps. This is a big pump. This is called a cryo platform. So as you are able to see here, this helps liquid nitrogen, liquid helium keep, not liquid helium, helium being cooled to 20 Kelvin be recirculated. Yet another thing that you are able to see here, this is called an auto sampler. What it does is that you can put 24 samples at a time, and the spectrometer can automatically, with a command from the computer that you type here, it can switch samples from here. So that's the only addition that you end up seeing. This is one example of how an experiment is set up. I already inserted a sample inside the NMR instrument, and first thing that I'll be doing is a step called locking. This is a field of frequency locking that is required in order to make sure any changes that come up in the frequency are properly calibrated for internally by the spectrometer. You carefully choose the solvent that is required. In this case, since we are using an aqueous solution with 10% or 5% with D2O, we end up choosing 90% H2O with 10% D2O in it. Moment you do this, on the right side of your screen, you'll be able to see the lock display that's trying to say whether the instrument is locked or not is going to give you an idea on what goes on. The first thing that you're going to see as a ringing in the next few seconds, you're going to see something that's going to ring up here. Keep watching. The ringing that you see here is actually the FID from the deuterium channel, and the red and the green are the real and imaginary part. And what it's trying to do is to see what is the area under the curve for the deuterium FID, and therefore keep it at the frequency of deuterium. Basically, keep it at the D2O frequency. That is the first step that is being done. So that's how lock works. The next part of it is to shim the magnet where if you open the necessary window where you would have the different shim files. Basically, you would shim, and then if you touch up Z, and it's going to be incremented in steps of 5. And what you're doing here is basically change the current in the coil, the shim coils that are present. So whatever buttons you see up top here are the different shim coils, and each of them have a polynomial dependence based on the spatial properties. For instance, the Z is a linear shim coil that will change the magnetic field above the Z axis in a linear fashion. Z square is polynomial, Z3 and Z4, Z5 are similar polynomials, so Z2 is quadratic, and you also have XY shim coils where the currents across the XY axis are also changed. So X indicates it's changing linearly along the X axis, Y meaning Y, and so on and so forth. So what you're essentially doing here is to change the current in the coil that are present with the magnet. So basically, what I'm doing here when I click plus is by changing the current, and what you're able to see on the right hand side is a change in the integral of the deuterium FID. So you're trying to maximize the deuterium FID signal. So therefore, anything that goes lower than wherever you started means you're going in the wrong direction. So for instance, if I do Z2 and then keep clicking, you're able to see that it's dropping off drastically. So on the other hand, let me try going the other way. First, I increase the value of the current. Now I'll try decreasing the value of current to see whether the shims are getting any better. So since they are more or less there, you would rather keep it there and keep iterating between Z1 and Z2, Z3, Z4, Z5. And that's a protocol that one follows in order to ensure that the shimming is done across the Z's and then followed by the non-spin X and Y. Since our experiments are going on gradients, we don't end up spinning the sample. If you spin the sample, then the shims across X and Y get better. So nowadays, there are easier ways of getting this done, which is called gradient-based shimming, which is what I'm going to do right now to give you an idea. One can do one-dimensional gradient-based shimming where the image of the sample containing water is acquired across, and the images are repeatedly acquired by changing parameters. So what I'm trying to say is to do 1D shimming based on the solvent default, where it'll be looking at the water signal, optimize it for the protons since we are looking at that. It's a good idea not to use higher order shims when you're doing automated shimming. And then I'm also asking it to tune the different axes of shims, meaning do Z followed by X, followed by Y, followed by XZ, followed by YZ, finally finish off with Z again to make sure things are fine. So the moment I hit start, you're going to see the entire protocol starts running, and the log channel gives you an idea what's going to happen there. So it's just preparing a log, and the moment it does that, it's changing the phase in order to maximize the integral, the deuterium FID, and you're able to see as the phase gets changed, the value of the integral keeps increasing. You can imagine this going from 0 to 100% for a given log power and gain. So what it's trying to do is to change the space a little by little. It's trying to see whether it can maximize the signal in the log channel. So once that is being done, the next thing it tries to do is to change the current along the Z-axis, which is what you're able to see, Z being changed with different values. Z minus 88 is what is going on. And what you're able to observe here is that the log value keeps increasing. So it will do until it keeps increasing, and after a point, the log value will decrease. Therefore, it goes back and forth in order to maximize the integral of the deuterium signal, and therefore try to lock it at that given, or rather shim it to that given extent. So entire idea here, as you're able to see, now it has moved from Z to X, and now it's trying to maximize X, and now X is done, and then it goes to Y. Generally, for a given set of coils, X and Y don't change too much if they are shimmed very well with a line-shaped sample. And the only changes have to be done for Z, little bit of X and little bit of Y, and XZ, YZ, and Z back up again. If you might remember, we started the log level around at this level, probably between 60 to 70%. Now you're able to see that's gone very close to 80%. The slowly count is 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Now, once it has done that, it's going to run a quick set of experiments to see whether it has improved the shims or it has reached desirable values of shims that are required. So that's what you're going to see up right now. So you might see here, once again, the log level increased beyond 100%. That doesn't matter right now. It's quickly running images of the water and trying to see whether it has optimized the shim value. So within the next few minutes, you're going to see this is going to be done.
and we will see whether we improve the shims by looking at the overall integral of the line shape. Now it's back to locking again, making sure the locks have been properly done after the shimming process. Remember, all these are iterative processes. You lock, you shim, after you shim, you try to lock back again. And what you're able to see finally is that the lock level has more or less not changed. So it's still going on, still trying to tune the face again. Initially tuned the face, went to Z, did X, did Y, did XZ, did YZ, back to Z, and then once again it did the lock. So it keeps going back and forth. Once again, it's trying to do with Z because all these shim coils are related to one another. Change in current in one coil will affect change in current in the other coil. So you can imagine these shim coils as tiny electromagnets that are set around the sample. And what you're trying to do here is to homogenize the magnetic field around the sample. So that's the entire idea that you're trying to do here. More or less, this is entirely done. And we are going to see that the protocol is going to complete very soon. Once again, trying to see what's happening with Z. And then it's done. So basically, it has improved a tiny bit. It's not increased as much. So the next thing that I would like to do here is to run a proton one-dimensional NMR spectrum. And the experiment that I'll be running is something called a excitation sculpting. Basically, you have the 90-degree pulse followed by a selective 180 on water and a hard 180 juxtaposed with gradients of similar kind. Since I am not dealt with in the class, I cannot end up discussing what's happening here. But it suffices to say, after the 90-degree pulse, all that we are trying to do is to suppress the water signal in order to make sure you have minimum water as your sample is at 1 millimolar, while water is at 110 molar, and therefore acquire a signal that is coming. In order to do this most efficiently, the first thing after having done the lock and shim is to do tuning and matching. What is tuning and matching? This is to ensure that the pulses that you're applying effectively get transferred to the sample and does not get dissipated at speed. This is one experiment which has been set up with all carbon, nitrogen, and proton channels in it. So therefore, the first thing that I'll be tuning and matching will be the nitrogen channel, which you're going to see as a V that's going to come up any moment right now. So it ends up loading different electronic components, as you're able to see the status on the bottom left. Once that being done, once the FID flash starts to come, you see a dip that is expected. And what we are trying to do here is to match the edge of the V to the red line. The red line indicates the Larmor position frequency of nitrogen given the V0. And if you see, there are two parts here, matching and tuning. Matching ensures that the reflected power, as you're able to see, I'm changing the y-axis here, the tip of the blue gets as low as possible. So if I change the match, if you're able to see, I'm changing it in one direction, the match is going farther and farther away, indicating that I'm mismatching more and more. Since I hit left and it ended up mismatching, I'm going to hit right for it to slowly start coming. So I'm going to keep doing this until the blue line goes as low as it should. See, after a point, it also starts to increase. So I'm able to see that the reflected power is able to reach somewhere around 50 units, and that's about it. You can't get any lesser than that. So once that being done, the next thing that you have to do after having matched is to tune, meaning that the frequency dip has to match with the red. So I'm going to move back. When I'm using the tune, generally people match first, followed by tune. So the tune is to ensure that the frequency nicely gets tuned up. Basically, you're looking at the tank circuit and you're trying to make sure the reflected power is the least. Yet again, it remains somewhere around 100 and the frequency is reasonably matched. So this indicates that the nitrogen channel is quite reasonably tuned and matched. One has to wait for a few seconds after having clicked, because all we are doing is to change, once again, some values in the software, but that ends up changing currents in different coils or actually make a mechanical movement to come. So do not click frantically, do it slowly and step by. Now, having done the nitrogen 15, the next thing is to do carbon 13. The moment I hit carbon 13, once again, you're going to see the V dip. What we have to do is to match the impedance and tune the frequency. That's what we are going to end up doing right now. So we have 2 minutes, it's going to end up loading. The moment FID flash comes up, and it's all ready to flash the V curve, which is called the wobble curve, also that's how it's called. In this case, what you're able to see, the tune and match are reasonably set, so I'm not going to end up changing this as much, given the fact that I know that this probe is very sensitive to small changes in any tune and match I do on carbon will end up changing a lot, and I know for a fact this is one of the best that we could achieve in the probe. So I'm moving on to proton. Now when I end up getting proton, we'll once again get the box curve the moment the FID flash starts to come here. So we wait for a few moments and then see how the warp curve looks for proton and end up doing matching first, followed by tuning. So this way, we ensure that the pulses end up delivering most of the RF to the samples rather than to heating. So if you're able to see that the match is rather poor, the tune is even farther poor. So I end up trying to match. The more I hit on the right, it's moving lower. I'm just clicking one at a time, never be in a hurry. So once it hits the bottom, that means that it has matched. So it starts to go higher. I'll try to match it a little bit more. Now the match seems reasonable. Then I have to tune. So therefore, I'm hitting the tune buttons, radio buttons, to make sure I end up matching the tune. So I can go more focused into it. The moment I hit one more, you saw that it went away. So you got to be patient with this. There you go. So it's more or less the dip of the V curve. What you see here is actually the proton FID because the probe is so sensitive. Therefore, you get a kink like that. I save the position of the tune match for the nitrogen, carbon, and proton. The moment this module exits, the first thing I would like to do is to do a quick one-dimensional NMR experiment. Let me show you how the spectrum looks. I just started it, and it will take about a few seconds. Once I start this experiment, I do not know whether the pulse is calibrated. We'll do that in one moment. The first thing that we are doing here is to look at the spectrum to see whether you get any signal. So it's just starting all the electronics. So this 1D will take about 20 seconds. And you can actually see the real-time acquisition of the FID in this screen if you click A6QU. And what you're seeing here is the FID is being collected as a function of time. And since the number of scans are increased, the signal keeps adding up. So this is signal averaging. This is an experiment that has 8 scans. Therefore, it does the same experiment 8 times to do signal averaging. Once it's done, since I have also entered the EFT command, it has also Fourier transform. This is an example spectrum. And one of the steps one has to do is to do spacing so as to make sure the absorptive and dispersive parts are carefully cancelled out. And if you see water is here, although water is at 110 molar, you're able to see that even the few millimolar DNA sample is clearly visible. Okay, so now that being done, this experiment is written in such a way where the first pulse, which is called P3, has a constant 1, which we can pre-multiply this pulse with, where we would end up multiplying it 4. So therefore, if a 90-degree pulse width is carefully calibrated, then multiplying this first pulse by 4 will result in a 360-degree, and therefore you get a 0 cross. So that's what I'm going to do. That variable is called constone. So basically, if it's set to 1, it's 90 degrees. Set to 4, it becomes 360 degrees. So what I'm going to do is to run this experiment for a 360-degree flip angle. So if my pulse width is properly set, you're literally going to get almost 0. On the other hand, if the pulse angle is a little shorter, the pulse duration is a little shorter, you're going to get negative intensity. And if you're going to have a positive intensity, that indicates that your pulse width is larger. So what is the pulse width we set? We set it at 8.35 microseconds. Now we'll see whether we get a 0 or what do we end up getting. So what you're able to see here is a small positive signal, but remember there are also off-resonance effects. The carrier is kept on water, so I'm going to be looking at this signal indicating that it's more or less 0, therefore the pulse width is reasonably calibrated. So I put this whole experiment back to 90-degree pulses and repeat it again so as to have the experiment available for me with the 1D, and therefore you end up getting the one-dimensional NMR experiment by inserting the sample, locking for field frequency changes that might end up coming as the experiment runs, and followed by shimming to make sure the magnetic field around the sample is more or less homogeneous, Once these are done, you end up doing tuning and matching to ensure your pulses are efficiently delivered to the samples rather than being cheating loss. Once the 1D is done, I'm going to set up the 2D experiment. Since the pulses didn't change, I'm going to repeatedly set the 2D experiment for one of the things that I'm trying to see binding for. So once I end up setting it up, I can set up two 2D experiments. So these are the two 2D experiments I'm setting, 346 and 347. 346 is a carbon QC, while 347 is a nitrogen QC. So I say run these two experiments. So ZG stands for 0 go, and multi-ZG means 0 go 2 experiments starting from the experiment that I am in. So when I say multi-ZG 2, it says it's going to run starting 2 experiments, the total experiment time is 3.5 hours. And if I start right now, the experiment finishes today, 2023, October 26th by 7:40 p.m. So this way we will be ready to set up the next experiment. The moment the experiment starts, the electronics get started, you will also see since gradients are involved, the lock channel will indicate whether the experiment is running. Once again, this helps you hopefully understand what are the processes that are done once the sample is inserted into the NMR probe. Okay, thank you very much.